We start by looking at the scenario of a sailboat and some wind that's blowing the sailboat that allows the sailboat to move forward on water. So for a sailboat to move forward and accelerate, we know that there has to be a net force. Now, how is this force being produced? And we're going to look at this in terms of momentum. So what we're going to do is we're going to zoom in on this little area here where the wind comes in, hits the sail. And we're going to pretend that it's a flat wall and that we have air molecules coming in with velocity v, and they are all of mass m, and that they have spacing of L between them, and that they hit the sheet and then they bounce back, avoiding each other with a velocity u. And they're also spaced out by L up here. So what we need to do is, since this isn't going to be smooth and continuous, but discrete bumps over and over again, we're going to look at the average mass that hits the wall. So this is the wall. So the average amount of mass that is hitting the wall in a time delta t. So we know that the amount of distance one of these will travel in a time delta t will be equal to its velocity times delta t. So we're going from meters per second multiplied by seconds and getting a distance. So this is the amount of distance traveled, and then the amount of distance traveled divided by the spacing, which in this case is L, gives the number of particles in delta t that hit the wall. So these are the number of particles in a time delta t that hit the wall. If we take this and multiply this by the mass, so if we say that this is now equal to n, if we do n times m equal average mass hitting the wall in delta t, and in this case that average mass will be mv delta t over L. So this is the average amount of mass that we have hitting in a time delta t. And what we also need to do is figure out the change in velocity. So the change in velocity, remember, is final minus initial. And in this case, the final velocity, so we'll say that going this way is equal to positive. So if we say going to the right is positive, then going to the left is negative. So we have minus u minus, and v is positive. This gives us minus u plus v. And to calculate the change in momentum that occurs in the delta t, we just multiply these two quantities together. So this is sort of our m times v. So our delta p equals to m v delta t over L. And now we multiply this by delta v, which is equal to, this now will give us m v delta t all over L times negative u plus v. So our delta p is equal to minus m v delta t over L times u plus v. Now to get the average force, what we do is we divide our change in momentum by our change in time. So the average force will be delta p over delta t. So what ends up happening is we're going to have minus m v delta t all over L times u plus v. All of this is over delta t. Where delta t's will cancel. We're just going to have minus m v over L times u plus v. And then this is the average force that is exerted on the massive particles. So this force, which I've called F-av, will be in this direction. So it's in the minus direction, so it's causing the change in momentum of the air particles to be towards the left. And then the force on the wall, or the sail of the ship, is just, by Newton's third law, going to be the opposite of this. That's going to be the same magnitude, but opposite direction. So m times v over L, u plus v. So does this make sense? So this is in the positive direction, so it means it's going to the right. We have a big gust of wind, the ship will accelerate to the right, so that makes sense. It's proportional to the mass of the air particles coming in, so if they're much more massive, then there'll be a greater force. That seems believable. It's inversely proportional to the spacing. So if L is really large, then that means there's a lot of dead space in between here. So it means that we have not much air. So this would say that a sailboat in outer space would not be an optimal way to travel, because you're going to be very infrequently getting hit by an air molecule. Now over here, this might be a little bit harder for you to see, but we have velocity times the addition of the two velocities. So this is always going to add up to be a number bigger than v, and then this is always going to be v. So really we're getting velocity squared. So really this looks something like the mass of the object times the velocity squared of the object, so it's sort of proportional to this over the length. So it goes as the square of the velocity. Alright, thank you very much.